Well, freezers are the lifeline, if you will, for much of the human research that takes place on the station. Crew members collect blood and urine samples, but they must have a way to return those to Earth at the proper temperatures. That's where something fittingly called Polar comes in. Polar units are being tested here at the Marshall Center. Like many other payloads before, Marshall has the facilities to simulate launch conditions and make sure that these payloads are ready for launch as well as operating on the station. I caught up with some of the engineers to learn more about Polar. I'm here in what's called the Shaker Room with Josh Dunn, and he is the systems engineer at the University of Alabama at Birmingham. And Josh, what are we doing here in the Shaker Room? You're testing something called Polar. What is Polar?
Well, Polar is a freezer that was designed and built by the University of Alabama at Birmingham, and it's the latest addition to the available cold stowage resources on the space station. And it's a small freezer. It's designed to fit within the single locker dimension requirements for express rack payloads. And to give some perspective on that, I would say it's approximately half the size of your typical mini fridge or dorm room type refrigerator. Operationally, it's got a temperature range that ranges anywhere from as warm as 4 degrees Celsius, slightly above freezing, all the way to negative 95 degrees Celsius.
So how does that compare to my fridge and freezer at home?
Well, I think the typical refrigerator at home is somewhere around 4 degrees on the upper end, and then in the freezer it's in the negative 20 range, so it's quite a bit different.
So this facility is really vital to human research. Tell us about what it transports.
So Polar's main purpose is transporting science to and from the space station, and there's really a wide variety of the science that could be stowed within it. It provides a generically designed sample volume, so pretty much anything that requires transportation in a thermally controlled environment can be stowed within it. Typically, biological samples such as blood and urine specimens are what is stowed, but it's certainly not limited to those types of samples.
So you're involved because you're an engineer at UAB and you guys built this. Tell us about the relationship between you guys and NASA.
So the UAB and NASA relationship goes back several years. The engineering division of our center began supporting development of protein crystal growth hardware for experiments on the space shuttle. And over the years, we've kind of evolved, and our main focus has shifted into the development of cold stowage payloads such as Polar and Glacier. And we also have another payload called Merlin, which is a freezer refrigerator incubator. I think we have 4 Merlins on board the station that are supporting everything from science to stowage of the crew's food and drinks in the galley. So we support payload integration and operations out of KSC, and then our contracts are managed out of JSC. So between the testing we do here at Marshall and the other activities at the other centers, we have a close working relationship with multiple NASA centers.
And now we're going to talk to one of your colleagues about the actual testing.
Okay.
I'm joined now by Aaron Reese. He is a mechanical engineer at UAB, and you're kind of handling the testing here of Polar. Tell us what the testing is. We say we're in the Shaker Room. What does that mean?
Yes, ma'am. We're doing vibration testing on Polar as part of the flight qualification process. Each unit is tested and analyzed to ensure that it meets the flight requirements.
So it's actual flight hardware brought here, and then you shake it.
Mm-hmm. We are able to, from shaking the unit, we impart a flight-like vibration spectrum onto the unit, and from that we can determine the resonant response of the unit and also quantify the workmanship of the production of the unit so we can verify that it was built properly.
Now, we're not talking actual vibrations like you feel at launch, are we?
Yes, we are. It's exposed to a flight-like vibration spectrum.
But not quite there, right? Not quite at that level.
We have a qualification unit that's exposed to over a qualification level vibration load, and then these are exposed to an acceptance level, which is slightly lower than that, to determine the workmanship of the unit.
So how long does this testing go on?
Each unit is tested. The vibration testing typically takes a day, and then we'll move on to different environmental testing. But we have to do it for 14 units, so it spans the entire production of the project.
So it's not just the shaker test. What else do we do?
We'll be doing acoustic testing, but we also come back up here to Marshall for different things such as electromagnetic interference testing and functional checkouts with a flight-like express rack throughout different stages of the production and flight preparation process.
Why the acoustic testing?
There are maximum noise limit requirements on the station to prevent the crew from experiencing unhealthy noise limits. So we've operate Polar at its maximum, its loudest state, and verify that we are not exceeding those limits.
So what's it like for you working with this actual flight hardware and really helping with the research program?
It's pretty awesome. I mean, it's great to know that one thing that we've worked on is going to be orbiting the Earth on the space station. It's going to be used to progress science, and we're incredibly fortunate to have this opportunity.
You stand there in Birmingham and you watch it fly over and you say, hey,
Yes.
I've touched a piece of hardware on that.
Absolutely. I mean, that's incredible.